Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss the Rayleigh-Jeans law and ultraviolet catastrophe. Let's begin. Rayleigh and Jeans, two scientists, proposed their law regarding the energy distribution of a blackbody radiation. As we have already known what is blackbody and how it radiates energy. According to him, the energy density, that is energy per unit volume within a frequency range, let we prefer that frequency range from nu to nu plus d nu is given by u nu d nu, that is the energy density in that frequency range is equal to 8 pi nu square d nu divided by cq into kBT. Energy density in terms of frequency. Similarly, in terms of wavelength, that wavelength range from lambda to lambda plus d lambda, u lambda d lambda, that is energy density of a blackbody radiation within this wavelength range is equal to 8 pi kBT divided by lambda to the power 4th d lambda. Let us discuss how to derive the Rayleigh-Jeans law. Derivation of Rayleigh-Jeans law. See the classical derivation. Rayleigh and Jeans derive by using classical mechanics and two assumptions. What are the assumptions? To derive this law, we have to assume that the blackbody radiator means a radiator which behave like a blackbody, as we practically use blackbody in our experimental purpose. Therefore, the blackbody radiator forms stationary waves of various frequencies. Let me clarify what is stationary waves. Stationary wave or standing waves, the type of wave is formed when we observe the waves that are bounded by a system. Stationary waves, that wave one point is fixed, another one is vibrating. Also, you say two waves and one is opposite to the direction of another, which is called stationary waves or standing waves. In that of case, from that of blackbody radiator, we consider the stationary waves of various frequencies. Why various number of frequencies? Due to the reflections of thermal radiations at the walls of the enclosure. The walls of the enclosure where we situate that blackbody emits the radiations, and that radiations are in the form of stationary waves, various frequencies, and they collide, or we can say strike on that of walls, as the nature of these frequencies is totally reflecting. So, these waves are reflected back from that of enclosure of the walls. What type of enclosure we have to consider? Suppose the enclosure is a cube and that cube having the side A. We choose the blackbody radiator as a cubical black body. The cubical black body which radiations with various frequencies range, and the size of that cube, let A, and that cube within the sphere, and to calculate the number of modes of vibrations within the frequency range nu to nu plus d nu, that number of modes of vibration is equal to 1 by 8th of that of spherical shell with the radii this to that. Since that one is a black body radiator in the form of cube, so the radiations are the wave just like stationary waves or standing waves, means the starting from one point and on colliding on that of wall of that of enclosure, again reflect back to that point, waves like stationary wave or standing wave, and that behavior is for one frequency range. Again another direction and reflect back, that one is another frequency range. Similarly, if that wave is in the direction of obliquely and again reflect back to that of position, it will be another frequency. So a number of frequencies are allowed, but to calculate what be the number of modes of vibrations in a particular frequency range, number of mode of vibrations means what be the number of allowed frequencies for a particular black body radiations. To show that, we have to consider a sphere through which that radiator is situated. In that of 3-dimensional scenario, we have to choose such type of sphere. Taking the sphere, this is in the 3 dimension, that sphere with radius 2a nu divided by c. At another frequency range, this is the frequency range what nu, that is the frequency range nu plus d nu. Within this is the allowed number of mode of vibrations. That radius 2a nu by c, this radius 2a nu plus d nu by c. How to calculate? Here, to calculate the number of modes of vibrations within that of frequency range nu and nu plus d nu, we have to take in the volume within that spherical region, and that sphere, inner sphere with radius 2a nu by c, outer sphere with the radius 2a nu plus d nu by c, and 1 by 8th of that of spherical volume is the number of mode of vibrations. Therefore, the number of mode of vibrations per unit volume with the frequency range, that is nu and nu plus d nu, is equal to 1/8 that volume 4/3 pi radius 2a nu plus d nu whole cube divided by c minus 4/3 pi r cube as the radius 2a nu by c whole cube divided by per unit volume was a cube. A is the side of that cube. Okay, how to solve it? Look here, in these terms 1/8 into, here we have to consider the common term as 4/3 pi, then this is the whole cube of that term. Okay, 4/3 pi common. In this term also we take common as 2a by c whole cube. Next, nu plus d nu whole cube minus nu cube divided by a cube. Now we solve it. Which one is 1/8 into 4 pi by 3, here 8 a cube divided by c cube into, now we expand it, a plus b whole cube, a cube plus b cube plus 3 a square b plus 3a b square minus b cube divided by a cube plus nu cube minus nu cube cancelled out, and the higher terms of d nu is neglected. Higher terms of d nu power is neglected. So that expression contain, look here, a cube in that of numerator side, in that of denominator side a cube also cancelled out. That term here, this term and that term as neglected, only this term exists. Now simplifying it, 8 cancelled out, a cube cancelled out, which one is 4/3 pi divided by c cube into, that is neglected, 3 nu square d nu. Simply we can write it 4 pi, here 3 cancelled out, 4 pi nu square divided by CQ d nu. This one is the number of mode of vibrations per unit volume within that of a frequency range nu and nu plus d nu. As we taken, this one is stationary waves. As I say, it's two waves, one is just opposite to another one, means in case of that black body radiations, the radiations are electromagnetic waves. They travel with the speed of light and these are transverse in nature. For transverse waves or as stationary waves, it has two possible polarizations for each wave. Therefore, the number of modes of vibrations per unit volume within that of frequency range now changed to 2 is simply multiplied. Since these waves are two possible polarization for each wave, therefore the total number of modes of vibrations between that frequency range nu and nu plus d nu range is equal to 2 into that result as 2 pi nu square, 4 pi nu square d nu divided by CQ, which is equal to 8 pi nu square d nu divided by CQ. Let us refer equation number 1. Rayleigh assumed one such assumption as that black body radiators form stationary waves of various frequencies is the one such assumption by Rayleigh-Jeans to show his law regarding black body radiations. Another such assumption as the black body radiations obey the law of equipartition of energy, the law of equipartition of energy. According to the law, the kinetic energy associated with each degree of freedom is equal to half kT. According to this law, here we have to calculate what be the total mean energy. According to this law, the total mean energy E bar is equal to kT, kV Boltzmann constant into temperature. Here that black body radiation is at the temperature T. Now total mean energy is equal to kVT. Therefore, the total energy can be calculated when we multiply that mean energy to that of expression of total mode of vibrations within that of allowed frequency range. Therefore, the expression for energy density we call it as energy per unit volume. Per unit volume within frequency range nu and nu plus d nu is given by energy density for that of frequency range u nu d nu is equal to number of modes of vibrations within that frequency range, which one is 8 pi nu square d nu divided by CQ into total mean energy kVT. Therefore, u nu d nu is equal to 8 pi nu square d nu divided by CQ kVT. Energy density in terms of frequency. Energy density in terms of frequency according to Rayleigh-Jeans law. Again, we can write in terms of wavelength. This is the expression. For Rayleigh-Jeans law. In terms of frequency. Expression for Rayleigh-Jeans law. Again, in terms of wavelength, as we know, frequency is equal to c by lambda. Therefore, d nu is equal to minus c by lambda square, its magnitude d lambda. Therefore, equation number 2. Equation 2 becomes So, energy density in a particular wavelength lambda to d lambda u lambda d lambda is equal to, in place of nu we substitute c by lambda and d nu as minus c lambda square d lambda. So, the expression is written as 8 pi divided by cq c by lambda whole square minus c by lambda square d lambda, that is the magnitude term, into kBt. Therefore, u lambda d lambda is equal to 8 pi kBt divided by lambda to the power 4th d lambda. This is equation number 3. That one is the Rayleigh-Jeans law in terms of wavelength. This is the expression for Rayleigh-Jeans law in terms of wavelength. Rayleigh-Jeans law in terms of wavelength. Okay. So, here we see what is Rayleigh-Jeans law for blackbody radiations. That is the expression for energy density in terms of frequency, expression for energy density in terms of wavelength, its derivation by assuming first it is an stationary wave, and then we assumed another assumption, the blackbody radiations obey the law of equipartition of energy. Expression for Rayleigh-Jeans law in terms of frequency, expression of Rayleigh-Jeans law in terms of wavelength. Now, we can draw the graph in between frequency and energy density. Look here, if we draw a graph here, if we plotting a graph in between frequency and energy density, that is frequency nu in x direction and energy density u along y direction. For a particular temperature T, experimentally, first experimentally for blackbody radiation we obtain the graph just like this. For a particular temperature, that is the graph. This one is experimentally curve. But by using the Rayleigh-Jeans theory, when you plot that graph in between frequency and energy density, by taking that expression, the graph is just like this. At this point, it is just same as that of experimentally curve, but at that point doesn't obey. At higher higher frequency, that not holds good. This one is the theoretical curve. Theoretical curve as per this law. That is a catastrophe in physics, and that type of catastrophe we observe in ultraviolet region, that spectrum of radiation, that type of catastrophe we see in that of ultraviolet region. Therefore, it is called ultraviolet catastrophe. Again, we can also say it as Rayleigh-Jeans catastrophe. In that of same way, if we plot a graph in between wavelength and energy density, similarly, if we plot a graph between wavelength and energy density, wavelength lambda and energy density u along y direction. This is the theoretical curve, sorry, this is the experimental curve for blackbody radiation. Again, by using that expression, we obtain at that point it's same to that of experimental curve, but then it's violet in that of ultraviolet region. As we draw the graph in between wavelength and energy density, and that violation or that paradox, we call it as Rayleigh-Jeans catastrophe or ultraviolet catastrophe. We can write. Now, what is the concept of ultraviolet catastrophe? The experimental curve and the theoretical curves in the graph show the similar result only for low frequencies. Look that curve, that is the graph in between frequency and energy density. At low frequency, that a theoretical curve is same to that of experimental one, but at high frequency, that energy density seems to be at infinity. But at high frequencies or at a low wavelength, the theoretical curve shows that the energy density may increase to infinity. At a high frequency or at low wavelength, the energy density may increase to infinity. Similarly, at low wavelength, the energy density may increase to that of infinity, whereas the experimental curve shows that after attaining the maximum value, the energy density decreases with further increase in wavelength. But in experimentally, for blackbody radiations at a particular temperature, when we plot the graph in between frequency and energy density, so after attaining a maximum value, then it undergoes decrease with respect to that of increase in frequency. Similarly, when we plot the graph in between wavelength and energy density, after attaining the maximum energy to that of lower wavelength, and then it decreases as soon as the lower wavelength is continued. Okay. Since that situation happens itself in a shorter wavelength, or that shorter wavelength in that of ultraviolet region of electromagnetic spectrum. In electromagnetic spectrum, there are various regions as infrared, visible and ultraviolet. So, the ultraviolet region is under that of shorter wavelength and higher frequency range. It has been named as ultraviolet catastrophe, or we can say it as the Rayleigh-Jeans paradox, that is a disaster in that of physics phenomenon, and that disaster is called as ultraviolet catastrophe. Since we observe in that of ultraviolet region such type of spectrum, we call that phenomenon as ultraviolet catastrophe or Rayleigh-Jeans paradox. So, here with the help of this video lecture we understand what is Rayleigh-Jeans law to that of blackbody radiations, expression of energy density in terms of frequency, expression of energy density in terms of wavelength, its derivation by taking the assumption these radiations are stationary waves and another assumption as these radiations obey law of equipartition of energy, and these expressions are derived. By using that expression we plot the graph between frequency and energy density. We see the graph just like this. By taking wavelength and frequency, again the graph is looking like this. So, it is an catastrophe. That type of catastrophe is called ultraviolet catastrophe. What is ultraviolet catastrophe? We see here. So, with this useful and informative notes, let me wind up the session. Thank you.